Okay, the next is that I should talk a little bit about transceiver experiments with and measurements from 1 megahertz up to 3.8 gigahertz using a Lime SDR. Maybe you know the Lime SDR. I have it in my box over there. I can show later. It's a very small piece of SDR system. Well, oh, this is not a Lime SDR, but okay, we get it. This is a Lime SDR. The Lime SDR is this one I used. I get it from a friend of mine just for testing, so I have to give it back the next time. It is possible to transmit, to receive with the Lime SDR, which has 2 receivers and 2 transmitters. And there's a Lime SDR Mini, which only has 1 receiver and 1 transmitter. Small systems for wide frequency range are they can be found in the market. It is the HRF. We had 2 basic talks of the HRF in the past SDR-A, when you, not only the past, maybe 2 or 3 years ago, and you will find the videos on our webpage in YouTube. They are famous using for hacking, GPS, military communication, and everything what you can imagine, also for some measurement. Then the USRP is very different. They had very different types with wide capabilities. I think this is the first device of this class. Types of devices are network, bus oriented or embedded with sync system on the chips. If I counted correct, it's more than 10 devices available at the moment, different devices. And they have different daughter boards for the USRP1 still available. Other systems are the Blade RF and of course the Lime SDR. So I want to go into deep. What are these connectors all for? Maybe when you are not comfortable with UHF, you think, what is that? It must be an SMD resistor or something like that. But these are the connectors. It is the MHF minus U, and they have 3 connectors for the receiver 1, 3 for receiver 2, 2 for transmitter 1 and transmitter 2. And they have a high and a low and a wide entry point. I only used out the upper half. The upper half is this one, and you will find here a mirroring in the middle. This is the transmitter here, the second transmitter, and well, you see the input, then the mixers with only 1 synthesizer, some programmable amplifiers, low-pass filters, another amplifiers, and the ADC. 2 ADCs for INQ, of course. And here we see the same for the second receiver or the first. And the transmitter is in the similar but reverse direction. DAC, low-pass filters, mixer, and amplifiers to TX1 out. This means band 1 and band 2. So if one thinks I can go from 1 hertz to 3.8 gigahertz, you see, you have to use both. It's not only with 1 output. What can we do with it? We can, of course, use it as a transmitter, receiver, up to 9 centimeter. So we have all bands from 50 megahertz. Most of the commercial available transceivers neglect that we have mostly in the Europe 70 megahertz availabilities. Most of them don't have 70 megahertz. So this one can do it. Up to 3.4 gigahertz. I show you a little bit about a VNA up to 3.8 gigahertz, not at 3.8 gigahertz, but similar. One can have a linear transponder of the whole band. Think of any ham band, and you can do it with a whole transponder. One of the broadest bands are 23 centimeters at the moment, and well, it's not less than 60 megahertz. And this can be done with the Lime SDR. Digital and analog transmitting can be done. Framework for development is mainly GNU Radio at the moment. There is a POTOSware as well, and well, I use GNU Radio. One can have, not for the ham radio, but for other use, one can have GSM base station or LTE base station if you like that. The GQRX is a very famous Linux receiver for it, and here you see some pictures of it. It's not very spectacular. Measurements in our laboratory are done with FSQ and ZVL, with spectrum analyzer and spectrum and network analyzer combined. So you see we have a measurement system. Prepare the measurements with GNU Radio is an example. When I started the first time, I had some problems to find out the right block from GNU Radio, and the first one which I applied, it doesn't function since I do not have the right parameters. And I have to look a little bit around, so I decided to make one screenshot of the right parameters that you can find out if it works for you. Here is an LNA. I expected RX1 high or low, but it doesn't work. Yeah, but LNA works. This is the output characteristic of the transmitter published by the vendor, and they show the ham bands, which they say, well, gain about 20 decibel output. I think, oh, this is nice. If it makes 20 decibel, we should measure it. And this is my measurements. And you see it's not 20 decibel. I have with a low band 10 decibel dBm at the maximum, and then it's decreasing after the bandwidth of 1.5 gigahertz. And you see for the high band, here we reach 15 dBm. Okay, that's okay. Well, you see it is dropping over higher than 3 gigahertz, but 3 gigahertz is still 8 dBm output. So it is done with measurement steps by 1 megahertz. Then we want to know what is below. Can we start with 1 megahertz? And I couldn't. You see the amplitude increases roughly when I'm at 25 megahertz. So 25 megahertz is okay. Below, I wonder if you have other experiments? Okay. So next step is to use a 1.28 gigahertz signal made from the TX. You see it's minus 12 dBm. minus 12, it should be minus 9 dBm. And this is a very good new, if you look on the 74 decibel is this second harmonic is 47 decibel below without any additional filters. This sounds quite okay, so that we can use it without more selective systems. TX band 1 on 200 megahertz looks not so nice. When you have I added an external attenuator, so I reduced the output gain a little bit down to the 50 decibel, and you see we have a lower output level. It's minus 19, plus 20 decibel means 0 decibel dBm output, but the second harmonics is only minus 10 decibel. This is too low. This is not acceptable for transmission without any additional filters. The FPGA features are, it's an Altera Cyclone 4 with a ball grid 484 pins, so you can imagine it's hard to solder by yourself. 39,600 logic elements, 1,134 kilobits embedded memory, and 116 embedded multipliers, and 4 PLLs. It's just for making an SDR system with it. The Lime software is out of the box, the Lime util and the Lime Suite GUI. We have updated the drivers and FPGA. Low-level software can be done with a Lime util. It's command line oriented, and we had a GUI with graphic output, read and adjust all parameters of the LMS 7002. Control of additionally hardware with GPIO, clock generator with SI 5351, and operate some modules, and I show you the output of one module. Here in Bremen we have a DAB plus radio station at 170 megahertz, and can I see it here? No, it's not inside. And this is an OFDM spectrum of the DAB plus, only just a small piece of wire at the input. It's quite okay. The system design is we have a GNU radio at the top, or maybe other radio applications. We need SOAPy SDR or the USRP emulation. Good news, the Lime SDR has an open source GitHub with an USRP emulation inside. I didn't try it out, but of course it looks quite nice. So this will be similar to the USRP. We need the Lime SDR API system, the USB driver of the OS. It is connected via USB 3, and then we have the Lime SDR. I show you a little bit of the GNU radio test with receiver. I used the SMHU generator at the frequency of 2450.5 megahertz. AM 100% with 5 kilohertz, 10 decibel microvolt with minus 3.6 microvolt is this level, and you see, well, the AM side bands, side lobes are quite good to receive. The FFT is with 8,192 points, and the sample rate is 2,000 and 48 kilo samples. Last of my slides should be about the Pi VNA for Lime SDR. There is Python application for the Lime SDR. It is from the website of the Myriad of the vendor. It is a one-port VNA which should operate from 0.2 to 3.8 gigahertz with segments. I explained you that we have different receiver inputs, different transmitter outputs. It needs some Python 2.7 libs, NumPy, Smithplot, and Cython. Who one knows Cython? Okay, yeah, I too. Cython is a C variant of Python, and it makes it much more faster. So you can write Python code, put it into Cython. Maybe sometimes you have to adjust a little bit variables since they are stored in another direction. And then you have a very quick Python program. It's very interesting. And you need to set up this Cython Lime lib. Yeah, the Cython Lime, yeah, okay. The Cython Lime library is quite easy. You have to say on the command line, set up, and that's all. Then you have to have a short. And when I used it the last days before the ham radio, I hadn't a short in the lab. So I used a screwdriver. Just pull it in the SMA connector, and it was not a good idea. I show you the results. When you start with a process, maybe for measurement from 100 megahertz to 1 gigahertz, pardon, from 800 megahertz to 1 gigahertz, it's 200 megahertz, you see that the calibration with the short takes 0.8 seconds per megahertz. It's stepping 200 times. 200 seconds is a total process time. And when you have a screwdriver in the SMA connector, you see, oh, are the 200 now over or are they not? So this generates two files. After you have did the calibration, then you can measure. And they ask you for the measurement. I made a measurement with a 50 ohm resistor, just to show you the results for what we can expect. It generates two files, and then you have another process. You have to calculate and save the S1P touchstone file, or to make some plots. And I show you the setup. You see a setup with a bridge or with a reflection coupler, a very simple. This is a mini circuits reflection coupler connected to the Lime. And here now is, as you can see, the 50 ohm resistor. The measurement of a match should be this point here. But because of the wrong calibration, it is not the point. And you see these spikes. This is because of the wrong calibration. I show you here. This is a reflection coefficient. And you see, well, here I'm a little bit nervous. I lost the contact. And then the calibration goes wrong. But one can see it's a good system for if you want to have a very cheap network analyzer. Out of the box, nothing to do else, just to have a bridge or reflection. Well, I want to conclude. Lime SDR USB evaluated from 10 megahertz to 3.8 gigahertz, but of course it is not sufficient for frequencies below 25 megahertz for me. Could be anyone else getting other results. One synthesizer each for TX and one for RX, but only one. This means 2 receivers, 2 transmitters are within a bandwidth of 60 megahertz fixed together. With SOAP SDR or USRP emulation works with GNU Radio. Lime Suite GUI is extensive tool for parameter optimization of the LMS 7002. TX shows less power than vendor's data, and the Pi VNA for Lime SDR works out of the box. Thank you very much for your attention. Any questions?
Are the measurements made with the last firmware? We had a big improvement of the firmware in April 2018.
Yes, I know. And if you start the Lime SDR, you are requested to reload the actual and the newest firmware from the website. So you are very sure I made these measurements the last days of May, maybe a week ago, and this is the version of the firmware.
Thomas Div20, did you modify the wideband input to accept lower frequencies?
No, I didn't anything, as I told you.
Board.
It was a board for
just
for testing, and it's not my own.
Your experience. Okay.
Yeah. So of course, I show you one of the slides, and you see these small connectors, and here. And if you see these small transformers, you can imagine if you exchange these transformers, you get better characteristics, whatever you want. But these transformers for the output are only for microwave. They are not for shortwave. Answer this question? Okay. Okay, other question?
Yeah. How do you get out of the SDR if it is transmitting or receiving? There's no transmit LED or anything to switch the PA if you want to use it for ham radio.
If you want to use it for ham radio, you have to use an external coupler for one antenna or to use 2 antenna.
Yeah. This part is fixed already, but without an Vox, I cannot detect if the Lime SDR is transmitting or receiving. There's no GPIO or anything to switch the antenna relays and the PA.
I think there are GPIOs. I didn't have the board with them, but there are small connectors on it, and
yeah, there are GPIOs, but there's no indicator if it's sending or receiving.
That's right. Yeah,
and
that's right.
Very bad.
Only the data transmission can be found at the LED lamps. There are some small lamps
for the data
indicating data transmission.
In comparison to the Hacker F, it has a TX LED, so I can use the TX LED for switching my relays and the PA on and off.
Okay, thank you. I think it is an improvement which I take with me.
Thank you.
Okay. Any more questions? Yeah. To? Good question. Thank you for the mini Lime question. I should say one of my colleagues ordered a mini Lime a few months ago, and the mini Lime was pronounced for end of May. Starting of May. So I said, well, fine, I can do the comparison. But up to now, there is no mini Lime in Bremen.
End of June, I think.
Okay, end of June. Hopefully, then we can add this. Any more questions? Or the next? Yeah? Okay. Thank you very much.